In this problem, we're dealing with a swimming pool. We're told right away it's supposed to have an area of 1,800 square feet. So I'm going to write that right in here right away. And then we're told we want 5-foot decks on either side. So 5 here and 5 here and 10 foot at either end. So we'll put 10 right here and 10 right down here. Okay, and we're supposed to find the dimensions of the smallest piece of property on which the pool can satisfy these conditions. So smallest implies that we want to minimize, and what we want to minimize is the entire area because the property holds the whole thing. So minimize the entire area. So we want a formula for area. Now right now we have no variables on here. We have a choice to make. Are we going to use a variable for this entire length or the inside? The entire width or the inside? Because they gave me the area of the pool for the inside, I'm going to introduce my variables for the inside measurements because that's going to make using that 1,800 easier. You could do it with your variables out here. It would still work, but we're going to do it this way in this video. All right, so to get the entire area, I need to find the distance across the bottom. That's going to be x and those 2 5s. So x and 2 5s gives us x plus 10. And here, this length up and down is y plus a 10 here and a 10 here for a total of y plus 20. So our entire area is going to be x plus 10 times y plus 20. And like we see in many of these problems, we have two variables and we can't. So we look for another clue, and that clue we haven't used yet is the 1,800. And we can see by putting the xy here, we can write an easy formula, x times y equals 1,800. It doesn't matter which one we solve for. I'm just going to go ahead and solve for y. It'll work either way. 1,800 over x, and I'll substitute it in here. So a equals x plus 10 and 1,800 over x plus 20. All right, our next step is going to be to find the derivative, but we have a couple choices. We could just jump in and do the derivative with product rule. I'm sure it would work fine. We could also decide to multiply this out first. I'm going to try that way. And so what I'm going to be using here is FOIL. Think back to Algebra 1. I'm going to use FOIL on this expression, and it actually does some nice things when we do that. Go back to my skinny pen here. All right, so when I take my first x times 1,800 over x, I get just 1,800. When I do my outer for O, that's x times 20, that's 20x. My inner, 10 times 1,800 over x is going to be 18,000 over x. And my last is 200. What I like about this is I end up with these two constants. And so when I take my derivative, dA dx, I get 0 plus 20. Derivative of this is negative 18,000 over x squared plus 0. There we go. We set our derivative equal to 0. We could choose at this point to multiply everything by, I guess we'll just get that 18,000 over x squared on this side. I'll just draw that 0 for that purpose. So there it is, equals 20. Well, it came over, so it's no longer negative. It's a positive 18,000. So now I've got 18,000 equals 20x squared. Divide by 20. 900 equals x squared. Yay, a perfect square. X equals 30. All right, so I found my critical number. Now I just need to plug it in to answer the question, which was the dimensions of the property. So let's see, 30 plus 10 is 40, so that's going to be 40 feet by, and I put in up here y. Oh, I need y, so let's see, 1,800 over 30 gives me y, which is 60. And 60 plus 20 is 80. So 40 feet by 80 feet. We've finished that one out.